Alright, so this is 5.4 poisson distribution. Alright, that's poisson as in the French way to say fish, not poison. Okay, now the poisson distribution needs two variables. It needs lambda, lowercase Greek letter lambda, and x. And this is the formula for it. E to the negative lambda multiplied by lambda to the x, all divided by x factorial. Now, you might be asking yourself, why not just move this downstairs because of a negative exponent? I don't know. That's how this book writes it. I've seen it written in a couple different forms. Now, x is a physical count for how many errors you are looking for. And here's where it gets a little bit weird. Lambda is the number of errors per your expectation. Right? It's the average number of occurrences. The thing is, it needs to be in terms of whatever you're looking at. More on lambda when we do an example for part 2. Now, just like for the binomial and just like for the multinomial, there's some criteria that must be met. Very specifically, the one I'm going to make sure that you check on is, it is an interval. All right? You're looking for the number of errors per page, the number of errors per yard of fabric, the number of people showing up during a specific hour. All right, the Poisson distribution is looking for occurrences that happen over some sort of interval. All right, you could be counting the number of wildflowers in a field, and you look at a little patch of it, and then you want to estimate the number of wildflowers for the entirety of the field. Okay, that's how the Poisson works, based off of intervals, the number of occurrences. Now, it needs to be independent and it needs to happen randomly. If you're thinking about a machine that makes cloth and you're counting the number of mistakes, it can't be that a specific roller keeps turning out the same mistake in the same place. Then it wouldn't be random. It has to be random occurrences of things happening over a certain interval.